This is the first introduction to integer programming. So in many situations it only makes sense if decision variables take integer values. And if we add that to the linear programs that we have already seen before, then we are in the area of integer linear programming. So an integer linear program is just a linear program, but then with the additional requirements that at least part of the decision variables can only take integer values. Two categories can be distinguished. Sometimes it's directly clear that we should use integer decision variables. If we talk about, for instance, the number of machines that we are going to buy or that we are going to use, then we cannot buy non-integer values of machines. So here there's a direct reason to use integer variables. It can also be that we have constraints that are non-linear, and sometimes by adding integer variables we can use a certain transformation to transform those non-linear constraints into linear constraints. So that's the second reason why it's useful to be able to solve linear programs with integer variables. A special type of an integer variable is a binary variable. So a binary variable is just an integer variable, but it's an integer variable that can only take values 0 and 1. And those variables are often used to model yes or no decisions. So we could, for instance, say that xj models a yes or no decision, and then 1 typically is the value for a yes, 0 typically is the value for no. Some other terminology. So we have pure integer programs, and we talk about a pure integer program if all variables are integer. We can also have mixed integer programs, and that's the case if we have both integer variables but also continuous variables. And binary integer programs are integer programs where all variables are binary, so where all variables can only take values 0 or 1. If we have formulated an integer linear program, then we can solve that by using Excel, and therefore we can use the int function in the Excel solver if we would like to restrict variables to integer values, and we can also restrict variables to binary values by using the bin function in the Excel solver. We are now going to consider this example of bus scheduling. So we have a table available here with the number of buses that are needed during 4-hour time intervals. You see that it's kind of a continuous schedule. It starts at 12 a.m. at midnight. It also ends at 12 a.m. and then basically the next day starts. So there are no breaks overnight. Each bus that we buy can be used for 8 successive hours a day only. So after using a bus for 8 hours, it cannot be used anymore during the remainder of the day. And we would like to determine the minimum number of buses that is needed in order to have enough buses available during each time interval. We are going to formulate this problem as a complete integer program. And then after that we will implement it in Excel, and then we use the Excel solver to determine an optimal solution. So the minimum number of buses needed and how those buses should be scheduled. First question is then, how are we going to define the decision variables? We could introduce a decision variable for each time interval that indicates how many buses we have available in that time interval. If you do it like that, then it's quite difficult to formulate the objective function and also to formulate the constraints. So it's easier if you define for each time interval a decision variable that indicates the number of buses that starts serving in that time interval. So let's write that down. So what we are going to do is we are going to let, and I just start with x1, we let x1 equal the number of buses starting at 12 a.m. And those buses will be available during the first time interval, but also during the second time interval. And likewise for the second decision variable, the number of buses that starts at 4 a.m. And then for each time interval we have a similar decision variable. So also for 12 p.m., for 4 p.m. and for 8 p.m. And we number them x3, x4 x5 and x6. So those are the decision variables, and I think that this is the most difficult step for this problem, because now that we have the decision variables, it's not that difficult anymore to state the integer linear program. So what we are going to do is we are going to minimize the number of buses needed. So we are going to minimize, and let's call that objective function z, and the total number of buses is just the sum of the decision variables. So it's x1 plus x2 and so on. This should of course be x5. So this is our objective, and then we have constraints, because during the first time interval we need 4 buses. And the buses that start their servers at 12 AM are of course available between 12 AM and 4 AM, but also buses that start one day earlier at 8 PM will also be available between 12 AM and 4 AM. So constraints, so subject 2, and then we will have x1 plus x6. This is the number of buses that we have available in between 12 AM and 4 AM, and this should be at least 4. The number of buses that we have available between 4 AM and 8 AM is x1 plus x2. That should be at least 8, and this structure continues. So then 10, 7, 12 and 4, and here we get x2 plus x3, x3 plus x4, x4 plus x5, and the number of buses available between 8 PM and 12 AM is then x5 plus x6. And then there's one more thing that we should not forget. We can of course not have negative number of buses, but we can also not have a non-integer number of buses. So what we will do as a last step is we will say that, so it's subject to this, and also subject to x1, x2, x3, x4, x5, x6, greater than or equal to 0, and also all integer. And this is a complete integer linear program that we can use to solve this problem. And now we are going to implement it in Excel, and then we use the solver to really determine the optimal solution. So what we have for this problem is 6 decision variables. So let's first set those 6 decision variables all equal to value 0, and then maybe in the top row it's convenient to also list the names of the decision variables so that we know what we are doing. And then the objective function is just the sum of the decision variables. So set value is the sum of the numbers that we have over here. So this is the number that we would like to maximize. That's the first step. And then we continue with the constraints. So we have left-hand sides that should be greater than or equal to certain right-hand sides, as you can see over here. So we have, for instance, x1 plus x6 is greater than or equal to 4. And it's very convenient to add these constraints by using a kind of matrix structure. So what we do here is we write a 1. So we are going to multiply the value of x1 by this 1. And we are also going to multiply the value of x6 by 1. That can be done by using the sum product rule. So we take the sum products of this first row and of this newly added row, and that is the value of the left hand side of the first functional constraint. The reference to A2 and to F2 should be fixed by pressing F4. So this is now 0, and this 0 should be greater than or equal to, 4 in the end. Then we also have the other functional constraints. So we also have x1 plus x2, we have x2 plus x3, x3 plus x4. So you see what the structure is. all left-hand sides, so we can copy this formula to the cells below. So here we calculate all left-hand sides, and those left-hand sides should all be greater than the right-hand sides. So what you see is that we have 4, we have 8, we have 10, we have 7, we have 12, and we have 4. This is then the set of all functional constraints, and maybe we can center this, looks a little bit better. And now we can use the solver to maximize the value over here. So if we give it a color, then this yellow cell should be minimized, and we are allowed to change the values of these blue cells. So then the next step now is that we are going to use the solver. So we go to data and then we go to solver. And then the objective is H2. So H2 should be minimized. We are allowed to change the values in the cells over here. And we have constraints. We have functional constraints. We can add those functional constraints at once. So these cells values should be greater than or equal to the values in these cells, element-wise. But if we add it like this, then we can add all constraints at once. So that needs to be added. There is more, because we also have an integer linear program here. All our decision variables can only take integer values, and that also needs to be added. So we are also going to add, and we refer to the decision variables over here, and then here we select int from integer. So if we add this constraint, then we will make sure that all decision variables can only take integer values. And we click OK. It's still a linear program, so we can still solve it by using the simplex LP methods. And then we can try if it works. So then we can hit the solve button, and then this is the solution that we find. Excel also tells us that it has found a solution, and then we can keep this solver solution. And then you see indeed that during each of the time periods we have the number of buses available that we need. Only in the last time frame we have much more buses available than we need, but that's because buses can be used for 8 hours. So you see also that in the optimal solution, in the last time frame we have 11 buses available, but we only need 4. Total number of buses that we need is 26. The last step is now that we go back to our mathematical model and to write down what the optimal solution is. So you see the optimal solution over here in Excel, and this is the optimal value. So let's also write it down over here. So we get optimal solution. We have x1 is equal to 4, x2 is equal to 4, x3 is equal to 6, x4 is equal to 1, x5 is equal to 11. And you see that in the last time interval we are not going to use any new buses. So in that last time interval we only use buses that start serving in the time interval from 4 to 8 p.m. So this is the optimal solution. The optimal value can also be added. So the optimal value to our problem is the total number of buses that we need. And if we go into Excel, then you see that that was the number 26. So this solves this problem.